why they're hard, what they can do now, and why they're the future. I would encourage you to just interrupt me as I go through the talk with questions. I think we're a small enough group that will work. And the talk is roughly structured course defined. So I'd rather clearly communicate the course parts than get to all the fine parts. Before I start, I'd like to call out people I collaborated with in this. This was a large collaboration over many years in different subsets of the projects. Especially most of the results I'm going to be showing you are due either to Luke Metz or James Harrison, so they should deserve almost all of the credit. Daniel Freeman has also been like a close collaborator in this for years and in a very helpful way. So in this talk, I'm going to try to convey maybe 3 themes. The first of these is that learned optimizers are starting to actually work. And in this talk, when I say learned optimizers, what I mean is a parameter update rule for a neural network, which is itself a black box neural network function. And just to drive that point home, let me show you a plot that we're going to come back to as maybe a teaser. So here the y-axis is the speed up of a given method over learning rate tuned atom, and the x-axis is the fraction of tasks on which you achieve that speed up. The set of tasks here is like 82 vaguely canonical neural network tasks that take like a little bit less than an hour each to run, held out tasks. And the biggest take-home message from this plot is that this nice red line here, which is our current state-of-the-art learned optimizer, is for almost all tasks significantly faster than other heavily hyperparameter tuned baselines. So for instance, this point says that we're 4x faster than learning rate tuned atom on roughly half of the tasks. This line here, which is maybe a nice one to compare against, is NATM-W, where we did 1,000 trials of hyperparameter tuning, including over learning rate schedules per task. And so these things are actually starting to work. I believe they will transform how we train models. There's maybe, if there's like one lesson we can take from the current deep learning revolution, it's that given enough training data and enough compute, learned functions will outperform hand design heuristics. But we still use hand design heuristics for our like optimizers and parameter update rules and to specify our loss functions and to choose our architectures. And I think we're getting to the point where we have enough compute and we have enough training data where training data is like optimization tasks that the learned functions are starting to work better. And maybe the third theme I want to convey is that despite the fact that these things are starting to actually work, there's lots of like just basic theoretical and experimental and like best practices style aspects of this that are completely unsettled. This is like mostly a greenfield research area, which I think is going to be transformative. Okay, cool. I'll pause here for like 4 seconds to see if there's a question. Oh, okay, Jesse.
So anyone who says we have enough compute in order that we can now,
yeah,
makes me scared as an academic.
Am
I going to be able to, in the academic context, take advantage of these tools?
Yes. Asterisk. So actually, I'm going to share a link at the end where you can like download the weights for the learned optimizer. That's the top line. Also, you can on a single TPU train one of these things, train a small learned optimizer to optimize a single task in like 2 or 3 minutes. So you can in a Colab kernel like experiment with these things. If you want to train one that can do this, then you need more compute. Okay, cool. Yeah. It is steps, but it is, I'll talk about specifically how we did this later, but the overhead for the optimizer is pretty minimal in this case. It depends on the problem, but it's probably like 10 or 20% change due to optimizer overhead. Cool. Yeah. It's sorted per optimizer. So we're just taking the same tasks and we're sorting them per optimizer by which ones the optimizer was fastest on and slowest on.
The other?
Yes, and I have one slide later that'll maybe show that a little bit, but we haven't really dug into that because it wasn't the thing we were measuring. Okay. All right. So I am, however, going to take a slight detour here to now that I've told you the TLDR of the talk, which is I just want to talk with you about your absolutely immense power that you have to shape the future. If you are sitting here in this room, then you have a lot of leverage in terms of how these technologies develop. And if you're at the interface of physics and ML, that doesn't mean you have less leverage. This is like one of the most productive interfaces. So this means you have more leverage. Yeah, so yes, you, the second-year grad student whose paper was just rejected, yeah, blah, blah, blah. For real though. AI is like transforming the world. I don't know how much you feel this, but this is going to seem like a process which is like beyond our individual control and is kind of scary. And this is a completely false impression. It is not at all beyond our individual control. AI is at the beginning of a period of like very, very rapid growth, and like small interventions that you make early in like an exponentially growing process can have like an absolutely outsized impact on the outcome. There's like countless examples of this in like science and engineering and technology, where like seemingly small choices lead to like vastly different outcomes. Like, I'm not going to go through these in detail, but like here, the first one, like a bunch of in 1980, like a group of scientists, like two scientists, proposed a standardized protocol for exchanging emails. And so you can send an email to everyone in this room. It was a decade later until someone tried to do the same thing for chat. And so you can only send chat messages to people in like the same little walled garden. There is like the choice of Dr. Gay to freely share with any colleague samples of the first the first immortal human cell line, HeLa cells, which was like a rapid accelerant on human biology, if perhaps like a little bit ethically like questionable because the cells were taken without permission. We can go down these, but basically, if you do something small at the beginning of something, it can like have a huge impact. And so the message is that like the individual small choices that you make in your research are going to determine the future like commercial and political and social landscape of AI and the world. Like things like, what research problem do you choose to work on? Do you open source your code? Do you find a new behavior and do you write it, call it a capability or a risk in the paper you write? Like what name do you give it? Do you choose architectures that are interpretable or not? Do you publicly share some kind of ethical stance? So you're incredibly powerful. You may not feel it. You may be paid shit, but you are incredibly powerful. And this is a responsibility as well. So like I have a call to action, and then I'll get back to the science, which is just be thoughtful about these decisions you make, because they really, really do have like rolling and growing consequences. Cool. I'm not taking questions in this part. So I've told you that you have immense power and responsibility, and that AI is going to change the world. So now let me tell you in more detail about a subportion of AI, which I think is going to be transformative, which is learned optimizers. So first, what is a learned optimizer? Let's say you have a model you want to train, and it has parameters W, and so you initialize it with parameters W0. And then you perform a step of SGD, of gradient descent. So you take your parameters and you subtract alpha times some learning rate times the gradient of your loss, and you update your parameters to W1. And you do this over and over and over again for like capital N steps until you think your model is trained. And then you look at the performance of your model. You look at maybe validation accuracy. So what we are going to do is we are going to replace SGD in this optimization process with a parametric function U. So U is going to take in the current value of the parameters and the gradients and what other information you want to throw into it. And it is going to have its own parameters theta. Yeah.
So it's a function of the gradient, but not of the loss itself.
You you actually have a lot of flexibility here. If you're going to emulate an existing optimizer, then it's a function of the gradient. You can just throw everything in there. You can tell it whatever you know about the problem, and it can be useful.
Yeah, I mean, the reason I'm asking is that in general, if we think about it in a physics language, say it's sort of Hamiltonian dynamics or even more general dynamical systems. And indeed, the generic case is where it depends on the loss and where that actually impacts its performance. So I was wondering, you're saying you could incorporate it, but I guess I should ask, have you yet incorporated that in your
Yeah, we actually the current the learned optimizer we have at head currently uses both the gradient and the loss value.
Okay, thank you.
Cool. Okay. And so we are going to call this process where you use the learn function U to optimize a model inner training. And so given the parameters theta of your optimizer, you use it to update W. And because we want this to be a learned optimizer, we also need to have an outer training or a meta training. And in this loop, we're going to take our measure of performance here and estimate the gradient of our measure of performance with respect to the parameters theta of the optimizer. And we're going to use that to update theta. And we're going to do that again and again and again until eventually we have thetas which correspond to an optimizer which does a particularly effective job at training the model. I'm going to pause here for 2 seconds for a question in case. Yes.
I feel like. Hello. So what do you use to update theta then? Do you just use the standard update rule, or is this a different?
Yeah, we will get there. That we will get to. Okay. Yeah. We'll get there too. Okay. So there's a lot of flexibility in what you choose for your function U, just so you have something concrete in your mind, and also because it's a simple case that reduces to most first-order optimizers. Let's imagine, until we discuss otherwise, that U is a per-parameter neural network. So U is a function that takes in a sequence of scalar gradients and outputs a sequence of scalar delta parameters. And so if you wanted to apply U, you would compute the gradient of your loss with respect to all the parameters in your network. You would vectorize this into one big vector of size number of parameters by 1. You would then treat that n parameters dimension like the batch and just apply this learned optimizer independently to every parameter and get weight updates for all the parameters and then reshape and just apply them to your weights. This is also nice because, as I mentioned, it reduces to first-order optimizers. So for instance, in a limiting case where your MLP here is just a linear mapping with no recurrence, then you recover SGD, where you have delta W is equal to some to your parameters theta times grad L, where your parameters theta is just your negative learning rate in this case. Cool. So this is just to have something concrete in your head when you think about what a learned optimizer could look like. Okay, so I've told you you have massive power and responsibility. I've told you what a learned optimizer is. And now I'm going to tell you all the reasons that they're actually really, really, really hard to train, and with some partial solutions to those. So the first of these reasons that they are hard to train is chaos. So we're now solving a bi-level optimization problem. Every single step of our optimization problem to optimize theta has an entire inner training system in it. And this inner training can have all the pathologies of dynamical systems. It can like diverge, it can be chaotic, it can like enter limit cycles, it can behave in lots of ways that you don't like. And it turns out that it's not just that your inner training dynamics can diverge. If you've ever tuned the learning rate for a model, you maybe noticed that like the best performing learning rate is typically as large as you can make it before your model blows up. This is a general property. The best performing hyperparameters for an optimizer are typically right on the edge of instability. So it's not just that you can have chaotic inner dynamics when you're doing your meta training, it's that your best performing optimizers will actively seek out those regions of chaotic dynamics. And we can illustrate that. So here, what I'm showing you is the meta loss you get for a 2D slice through the optimizer's parameter space theta, for an optimizer that's like partway trained. We're training this optimizer to itself train a 2-layer MLP on MNIST. So it's being trained to do one specific task, and it's like a variant of the per parameter learned optimizer I showed before. And so to start with, we are just going to apply our optimizer for one step. So this is the so here, this is the final training loss after you've used your optimizer to do one step of optimization on this 2-layer MLP and MNIST. And you can see this is a relatively smooth loss landscape. If you were going to do gradient descent of theta, you could start in one of the bright regions and do gradient descent and go to one of the dark regions. Now let's see what happens as we allow the learned optimizer to do more and more steps of optimization. So here is 2 steps, here's 3 steps, here's 5 steps. You can already see some structure. Here's like 7 steps, 10 steps. You get this like maybe like filamentous like complex structure in the meta loss landscape. 13, 15, 18, 20, 25, 30, 40, 50. And so at 50 steps, your meta loss landscape changes on a length scale, which is like shorter than the pixel discretization of this image. If you tried to do gradient descent on this loss landscape in order to optimize theta, you would completely fail. You get stuck in valleys, you'd get gradients that are like 10 to the 30. And of course, like 50 steps is short. Like you probably want to run it for like 50,000 steps or 50 million steps. So this makes the meta optimization process extraordinarily difficult because the surface that you're trying to do optimization over looks like this. I'm going to pause for 1 second here. Okay, chaos. So I can share our current best solution to this, emphasizing again that this is still like an open problem, which is like we're looking for better solutions. And the current best solution is to smooth this outer loss landscape before optimizing. And if you maybe squint in this image, you can see why that might work. If you were able to like blur, like convolve this image with a smoothing distribution, then you would be able to descend from like a bright region to a dark region. It's only this like high frequency structure that makes it impossible. So what does that mean? In order to smooth this loss landscape, we're going to define a new loss, fancy L of theta. And that new loss is going to correspond to of averaging L of theta over small perturbations of the parameters. So you're basically just defining this like perturbation distribution and convolving your loss landscape with it. This is awesome because it suppresses all the high frequency structure in your hinged optimization. It sucks because we don't have any closed form expression for like your loss landscape convolved with a Gaussian. In machine learning, if you want to take a gradient of something which you don't have a closed form expression for, if you want to take a gradient through an expectation, there may be like two stereotyped approaches that you use to solve this. The first of these is that you apply something called the like score function trick or the reinforced gradient estimator. And if you do that here, then you end up with a gradient estimator called evolution strategies, which is a finite difference gradient estimator, where you draw perturbations from epsilon, and then you compute the difference in loss at theta plus epsilon and theta minus epsilon, and then multiply by the epsilon direction. I'm going to make one super technical note here, which is that people often will write the ES estimator using only this first term and getting rid of the factor of 2. I've written it in terms of antithetical samples for 2 reasons. One, I think it makes it super clear it's a finite difference gradient estimator. But 2, if you compute ES with antithetical samples, it like cancels out the leading term in the variance in your gradient estimator. And it's the difference between something which like simply will not work at all and something which will just give you really, really high variance gradient estimates. So if you ever use this, you would really need to do this if you want it to work. The other approach that people use to take gradient estimations through expectations is the reparameterization trick. So in that case, what this means is you once again draw samples of the perturbations, and then you just average the analytic gradient taken at like theta plus that perturbation. These two gradient estimators have very different properties. If your loss function is smooth, then the reparameterization gradient is analytic and gives you much, much, much lower variance. On the other hand, if the loss surface is high curvature, then every analytic gradient is going to point in a different direction, and you're going to get a lower variance gradient estimate via the finite difference technique with large perturbations. You can see this illustrated here on the right. So here we're moving along a meta-training trajectory for training an optimizer. So the x-axis is how far you are through meta-training, and the y-axis is the gradient variance for these two estimators. And at initialization, you like initialize your learned optimizer in a good spot of the space. And at initialization, you have like an analytic gradient with like variance 1e -5, which is quite 10 -5, which is quite good. But then over the course of optimization, the learned optimizer is like attracted to this like edge of instability region, and your gradient variance increases by like 30 orders of magnitude. On the other hand, your evolution strategies gradient is like absolute crap at initialization. It has like variance 1, but it is just as crappy with variance 1 at the end of inner training. Cool. Okay, so problem number 1 is chaos. That maybe leads very naturally into problem number 2, which is just like outer training is extraordinarily expensive. If you think it takes capital N steps to train something, now you're doing capital N steps of training inside each of your capital N stress steps. And so you've gone from like N to N squared compute cost. On top of which, ES is a finite difference gradient estimator, so you should expect it's like has a variance, which is, you should expect you need a number of samples, which is like larger by like roughly number of optimizer parameters in order to get an equivalent variance gradient. can give you a partial solution to this, which is to use partial Unrolls, which I think is what Jesse was asking about earlier, which is rather than running the inner problem all the way to the end and computing an outer loss and the gradient outer loss, you can instead run the inner problem for like 2 or 3 or 10 or some small number of steps and compute an intermediate outer loss and then take the gradient of that outer loss with respect to those few steps. And then do it again and do it again. On its face, this would seem to be horribly biased because, of course, the outer loss after one step, after one set of Unrolls or 2 sets of Unrolls, is not at all the same as the outer loss you get at the end of inner training. And additionally, it like drops terms from gradient. So for instance, the way in which the W6 here depends on like your parameters theta during this first Unroll get like dropped. Somewhat remarkably, and I have an entirely different other talk I can give about this, but somewhat remarkably, you can compute correction terms, which you pass a small number of correction terms, which you pass forward through this sequence of Unrolls, such that by the time you've done all of the Unrolls, you get unbiased estimates of the gradient with respect to the entire inner training problem. You can do this both for evolution strategies. There's also analogous techniques that you can use for various like stochastic analytic gradient estimators. This is kind of magic, but I'm also not going to dive into it. Yes.
Just as a clarification, are you using an ensemble of networks essentially to evaluate the loss for the optimizer?
Can I just say it again?
An ensemble of networks essentially for the
You're asking like what is our meta training and meta test distribution?
Yeah, so in the meta training, are you using multiple networks? And does that, I mean, that might address also the reducing the noise effectively in the first problem, but also
yeah. So let me you can decide like maybe what you want to do is, of course, you want to train on things that look like what you're going to test on. So if you want to learn an optimizer that works in everything, then you want to meta train on as diverse a set of optimization tests as possible. If you want a learned optimizer that's really good at optimizing 3-layer convnets, then you want to meta train on a distribution of 3-layer convnets with different data needs. So yeah.
That's what you do, right?
Yeah. Cool. Okay. So this helps. You get more outer gradients, but you're still using a finite difference gradient estimator, which is horrible. Cool. I'm running. Is that my main talk time or is that the total time? Okay, and then there's. Okay, and I'm taking questions during, so hopefully. Okay, cool. I will panic slightly less. Cool. Another huge problem in learned optimizers is meta generalization. Like you probably want to learn an optimizer that will work on new tasks. In standard deep learning, the way in which you achieve this is you have large diverse data sets, and the like larger and more diverse your training distribution, the better you generalize to new tasks. We also have architectures like convolutional neural networks or transformers that have really good inductive biases for reasons that are still somewhat mysterious for most of the tasks that we do in practice. In deep learning, the first of those is a lot of work, but is relatively straightforward, which is you need to construct a large data set of optimization tasks. And similarly, you can construct a large set of like augmentations that you can apply to optimization tasks, like rescaling the loss function or automatically reparameterizing the problem, or changing noise levels in the gradients, or et cetera. And reassuringly, this does what you would hope. As you increase the size and diversity of your outer training set, then in fact, you do generalize better to new tasks. There is a caveat, however, which is maybe my biggest frustration with learned optimizers right now, which is that this won't allow you to generalize across scale. So What you would like, at least if you're me, is you would like to be able to meta-train a learned optimizer and then use it to train like a 1 trillion parameter language model for like, millions of training steps. And the difficulty with that is that you can't include very, very large models in your meta training set because they're simply too expensive to meta train on. So there's this like generalization access to much larger problems, which is still unsolved. It may be that finding the right parameterization, like maybe we should just be using like mean field or mu-p or similar like standard parameterizations or like incorporating those into the definition of the optimizer somehow. And I'll show some examples of generalizing across scale in a second. But otherwise, this seems to work well. In terms of architectural themes, I'm actually just going to mostly skip these. The short version is we have some like initial steps towards building in the right inductive bias into the architecture. You have to worry not just about how effective an optimizer is, but also what the overhead of the optimizer is compared to the actual task you're optimizing. You can do things like stability analysis of the joint Jacobian of the optimizer and the problem you're optimizing, and like look at the eigenvalues of that, and like try to find interventions that pull those eigenvalues towards 0. And there's various stuff you can do, but it's really an open problem. Like we don't have the right architecture yet. So one of you should come up with it. Cool, yeah. Okay, so I've told you of massive power and responsibility. I've told you what a learned optimizer is. I've told you a bunch of partially solved reasons why these things are actually still quite hard to work with. I'm going to show some pretty plots before I do that. Are there any questions on that last section?
So I'm not quite clear on the benefit of using evolutionary strategies here. Like I use evolutionary strategies because I do not have like easy access to gradient information. But wouldn't it just be better if you're using something like a neural network where you have like gradient information is pretty much just as cheap as forward passes, that you just do more samples of the gradient and like increase the variance of your normal distribution?
The problem is that the analytic gradients are like order 10 to the 30 or 60 or 90 or 200. Their analytic gradients are just so high variance that they're unusable.
Okay.
And here, if you remember, so this is the meta-loss landscape. The thing to observe on the meta-loss landscape is that as you unroll the optimization longer, as you apply the learned optimizer for more steps, the final solution the optimizer finds becomes more and more sensitive to very, very small changes in the optimizer's parameters. And you can see this even in first order optimizers. If you take like SGD or Atom and you look at the solutions it finds, if you like change like the third significant digit in the learning rate, you'll find it finds like completely different solutions. So because the solution your optimizer finds and just thus your meta loss then is like nearly discontinuous with like very, very small changes in the parameters of the optimizer, the gradients are just super high variance and you can't use them.
So how do you know the good step size for evolutionary strategies then? Like, isn't that a choice?
Oh, that's like a meta hyperparameter. It's relatively robust to this though. Like, but that's like same as setting the learning rate for learning theta. You also have to set the variance of the ES estimator when learning theta.
Yeah, if I can, one quick follow-up. For like this is assuming like you're using like a gradient-based like local optimizer, right? But you're running into a lot of these problems with like your bi-level optimization is really ill-defined for using a gradient-based optimizer. So if people tried things like, I know typically they don't do it because like it causes extra instabilities, but like a learned global optimizer.
Well, I mean, do you mean like use a learned optimizer to train the learned optimizer? Is that what you mean? Or do you mean like
No, like using like you're optimizing for your optimizer parameters.
Yeah.
using not like, because you're doing like a gradient-based method.
Oh,
on a
using
gradient.
like a black box search. I mean,
Yeah.
in some ways, that's like the standard way people do this, right? Like if you have a if you have a optimizer that has like 10 hyperparameters, you're probably doing random search on those hyperparameters. Right. And the problem is that scales very badly with like the number of hyperparameters or the number of parameters the optimizer itself has.
Okay.
Oh yeah.
So this feels very much like a reinforcement learning problem. You even use the word reinforce in there, which makes me think that it's like similar strategies where like each game that you're playing is basically training a neural network, and then you're updating your meta parameters again. Is there a similarity over there, or am I just?
Yeah, there is. You could use RL to try to train your learned optimizer. There's actually a thread of work that does that. It hasn't worked great for them so far, but there's a lot of reasons that could be. But you could totally use an RL approach instead of like a gradient driven approach to train the learned optimizer.
So that's a follow-up question, the question we just had over there. If you look at the minima that the neural network finds as an optimizer as compared to SGD or so, is there a qualitative difference in terms of, let's say, the largest eigenvalue of the hashing or something? That do they find shallower or wider or whatever types of minima after training, or is the variance just too big to say anything sensible about that?
We haven't looked at this in enough detail. There's some specific cases where they definitely do qualitatively different things. All right, let me give one example, which hopefully is not too much detail. One example is I mentioned that these have difficulty training very large models. When we first tried using one of these to train a billion parameter transformer, like it seemed to be training fine, and then it started nanning out. And we dug in, and what happens is the transformer has like layer norm and all these layers. And so the scale of the parameters doesn't matter before the layer norm. And that doesn't really matter for normal optimizer because it's gonna roughly maintain the parameter scale. But the learned optimizer was just like growing the parameter scale over the course of training. And if you have a large enough network, then you start getting floating point problems when you allow the parameter scale to just grow in an unbounded way. So there's a situation where it was clearly like choosing a quite different path than a vanilla like optimizer would, in this particular case, in a negative way than a vanilla optimizer would have chosen. But we haven't dug into this deeply enough.
Thank you.
Let me show some plots, and then we'll have time for more questions, I promise. I'll do this fast. Okay, so most of the plots I'm going to show are from VeLO, which is our current state-of-the-art general purpose learned optimizer. I'm going to say now because I might run out of time at the end. We have code, we have weights. You can find this on GitHub. You can apply it to your problems. I will bet you $1 that if you have some problem with less than 100 million parameters and you're training it for less than 100,000 steps, then we will match or more likely just outperform whatever your current optimizer does. This actually works. So I'm going to focus a bit on the ways in which it doesn't work, but it does actually work, which is exciting. So our goal was to create one versatile learned optimizer that works for all neural network training, outperforms all current optimizers, and requires 0 hyperparameter tuning. We trained across like a very wide variety of diverse tasks, and we used a lot of compute. The architecture is a little bit interesting. What you want to do is you want to minimize the overhead of the learned optimizer while at the same time maximizing its expressivity. And one way to do this is with a hierarchical optimizer, where the optimizer has a tiny little bit of compute for every parameter in the network you're training. and then a larger amount of compute that it can spend for like blocks of parameters. And I'm not going to actually talk about the details of the hierarchical architecture. I'm just going to say that you can structure this in such a way that the overhead per parameter is tiny, but the learned optimizer can still do relatively complex calculations that are like shared by many parameters. Okay, here is performance on the ML Commons init to winit workload. This is a benchmark that's still being formed, but it's about to be a benchmark. This is like the baselines are all from the ML Commons group, not from us. Each of these tasks take, I think, about an hour to run probably. What's nice is we do as well as the best baseline in 5 out of 6 problems. Here, the 2 red lines are VeLO, and VeLO can be told how many steps it's going to run for. And so here we just told it to run for a smaller number of steps, and you can see that it like does something analogous to decaying the learning rate earlier to account for the shorter training budget. There were no graph neural networks in the meta training set, and so this is an example of how when you apply a learned optimizer to something that's out of the meta training distribution, it can struggle. It's still comparable to maybe other hyperparameter runs, but it does significantly worse than otherwise. I already showed you this plot. You can also look at the cases where we did best and worst compared to other optimizers. It's maybe nice that even in the worst plot, we do like roughly comparable to others. I'm going to go through this fast. You can do phenomenology. We can make efficient use of large batch sizes. I think maybe more interesting than that is looking at failure cases. I already mentioned that when you try to use this, when you try to generalize across scale, it really struggles. So here we're using it to try to train an 8 billion parameter transformer. And in dashed blue is just the like baseline default hyperparameter technique in this code base. And in red is us. And you can see that when we apply it at the scale, training goes unstable and finds a significantly worse loss. There were no RL tasks in the meta training set. And if you take Atom and apply it to an RL task, it works fine. So for instance, here you can apply Atom to do like PPO training in an Ant environment, and it does great. When you try VeLO in this context, it saturates and doesn't do well. It somehow gets confused by the RL environment and just stops moving the parameters. There's also, this is slightly older version, but just a note that you can use learned optimizers also to solve problems in physics or physical simulation. So for instance, here, they're trying to find like low energy atomic, low energy ground states arrangements of atoms. And they're using a learned optimizer to do that. And the learned optimizer lines are below the baseline lines. Cool. Okay. There's a bunch of other approaches people can take to learned optimization. I'm trying to decide how much detail to go into. I'll do this. Okay. So maybe one thing that's really neat is your meta loss can be something totally different than your training loss. So your meta loss can be, for instance, how well do your representations perform on a downstream task? Or your meta loss can be the validation loss, or it can be anything. So it's nice because you can meta train an optimizer to target something completely different than what you think you're targeting with the training loss. You can use RL rather than ES to meta train, mixed success. You can kind of go partway down this path and like rather than training a full unlearned optimizer, instead train a controller for the hyperparameters of a standard optimizer. You can take a really different approach, and rather than trying to replace an optimizer, you can try to build a generative model of optima in the meta loss landscape. And then optimization is now sampling from that generative model of optima. In this case, they have like a diffusion model conditioned on the gradient, and that is which I think is like super cool. You can try to learn symbolic rather than black box neural network optimizers. You can try distillation as a training technique. So rather than trying to learn a totally new optimizer, you can take a hand design optimizer like Atom, and you can maybe try to distill 10 steps of Atom optimization into 1 step of learned optimizer update. And that is somewhat effective. And you can try to do meta learning in a totally online way rather than in a like amortized pre-training way. Cool. I already talked about this. So thank you. There's a link for code. Again, you can run small problems in like a few minutes in a collab, although large problems are large. Yeah, thank you so much.
I'm curious if you can interpret your optimizer in the end. Can you do something like symbolic regression on it or something to try and interpret what it found? I would personally like to see it in the language of Hamiltonian evolution, if that's a possibility. But
yeah, so I don't know about so let me two-part answer. In terms of Hamiltonian evolution, I doubt that it looks like a conservative update field, which I think if I understand your question, would be required there. So I suspect it's like a dynamical system, but it probably you probably could not find a Hamiltonian that the optimizer dynamics themselves respected.
yeah, that makes sense. That's a generic case. So.
Yeah. In terms of interpretability, we actually have a paper trying to dive into this. You can look for the kind of behaviors that have been useful for in hand design optimizers and see if the learned optimizers learn them. And for basically every behavior we looked for, we found evidence of a learned optimizer doing it. Things like gradient saturation or clipping, things like momentum and multiple time scales, things like adaptive learning rate normalization. But what you really want is to find the things that the learned optimizer is doing that we don't currently know to do in hand design optimizers, and that those are harder to identify. Like it's really like science to go in there and find it.
Right. Sorry, can I indulge with one more version of the question? So suppose you decided you wanted to consider the Hamiltonian case and do your optimization within that class. Has that sort of thing been tried? Because it's still an infinite functional space that you would be
yeah. So I guess I don't know if this exactly matches your question, but one thing you could do is rather than meta learning the parameter update rule, you could meta learn the loss function, and then you could descend the loss function with whatever integrator you wanted to use. And that would enforce it. I think that would be a reasonable thing to do. I think it's less flexible for roughly the same amount of compute, but it might match the system in a useful way. I haven't thought deeply about this. Yeah.
Yeah. So my question is a bit following up on this. This was on how we should think. What's your perspective on how we should bias our optimizer network or whatever? In particular, as you said, okay, so you see that it rediscovers certain strategies that have been before. But on the conceptual level, should we, go towards things that we have not realized perfectly, say things like natural gradient descent or things like that? Or should we think out of the box? Or is there some guidelines that you would think on, how we should go about biasing this?
Yeah, I mean, I think you want to build in as much useful structure as you can, and then give it the flexibility to move away from that if it wants to. So for instance, we do things like we make the updates proportional to the parameter norm, so that as you change the scale of the problem, it still does something by default relatively sensible.
We are out of time right now, but feel free to keep chatting, obviously. It is lunchtime, however, for those who want to leave. So you could do that. Thank you for your attention.